So thanks very much for the opportunity of having me along here. I think, like a lot of you on the webinar today, one of the silver linings of the whole COVID period has been the proliferation of some fantastic online learning opportunities and not having to drive into the city to access some of these things. So I've certainly appreciated them, and it's really great to be a part of it and to be able to present a topic that I'm really passionate about today. So I'm talking about the timber framing components for mid-rise that we can make off-site. And for us, it's in that sort of 3 to 4 story range, or more the upper floors of mid-rise buildings, as I'll get into later. So a little bit about me. I would say I'm not the conventional timber expert that you're used to seeing on these webinars. I have been in and around engineering roles for about 12 years now, a mix of technical and sales roles. And I think that's sort of part of what I hope to be able to bring today, is that I have done the nuts and bolts numerical work around engineering, but also done some of the selling work. And that's what I want to get onto later after I sort of explain some of the timber options, explain how you compare and contrast to what else is out in the market. And so, like Paolo mentioned, the last 4 years I spent at Ramsay Reed, and I was actually advocating for precast concrete. So I think that's a little bit of a different perspective, and I was brought into the Prida team not as a timber expert, so certainly to become one in time, but I guess that's my confession up front, is while we have some amazing timber experts at Prida, I was brought in because I have a little bit of a mix of knowledge. That's really what I want to bring to the presentation today, as well as the content about the timber solutions, is understanding what else is going on in the market and how does timber compare and contrast to other things, and particularly the concrete solutions. So outside of the professional world, a father of 3 young children. They're being looked after by someone else today, so we won't have any interruptions. And passionate road cyclist. I think the road bike is probably close enough to my 4th child based on the amount of the time and attention that it gets. So today, I'll very briefly talk about why timber. Obviously, there's a lot of resources through Wood Solutions already on that topic, and if you're here today, you've probably already got a leaning towards using timber solutions. I do want to talk a bit about why offsite manufactured systems are advantageous, what's available in that space, and also, how do they compare to particularly the concrete alternatives for these type of projects. So in terms of why timber as a material, I won't spend a lot of time on it because there are already some excellent webinars and content out there, and you only need to go to the Wood Solutions website, have a look at the Ultimate Renewal campaign to see all the benefits the building with timber brings. On a personal note, and looking at my career path, I'm actually really appreciated coming into this world in 2020, and it's always been fun as an engineer to have a role in creating the built environment, but this is really the first job I've had where actually it feels like not only am I contributing to that, but I'm doing it in a really sustainable way. And I think that's really a really important message, that as engineers we can create, we can build, but we can also do it in a way that's environmentally responsible. So why use offsite components versus site built? So number one, safety. So building offsite means you are working in a controlled environment. You're doing processes that facility is specifically designed to do, and so you've got repetition there. You've got formal processes in place to ensure that the right sequences are followed, that you can control that process a lot better than in an on-site environment. It also means you're taking work off site where things are less predictable. You're exposed to the elements and things like that, and it means that you're working at ground level fundamentally. So particularly on these projects getting up to quite significant heights, and the risk of falls becomes a significant one. Being able to work in a controlled environment at ground level is particularly advantageous. Offsite solutions are renowned for quality. Again, that controlled environment, the repetition of processes allows for a great deal of precision. And when dealing with timber elements, you can cut and you can connect in extremely precise ways and have everything ready to go and fit perfectly when it gets to site. In terms of speed, we do see huge advantages for when components get to site. So versus trying to fabricate and install on a site, essentially creating systems that are drag and drop, so off the truck and into place. removes a huge amount of labour from site, and we know that's where a huge amount of the cost of projects comes from. There are some compliance advantages to building offsite. So there's some really smart software that sits behind a lot of the solutions I'm going to be talking about today. And that software and the development that goes into it and the engineering sign-off that backs it actually absorbs a huge amount of the compliance responsibilities that we have on projects. And so you can really see if you're a certifier coming in, it's very clear, very traceable back to the requirements of the NCC, the requirements of the Australian standards. And finally, and fundamentally, simplicity. The whole ethos of offsite and prefabrication is that you front load the project and deal with as much of the complexity as you possibly can before anything even gets to site, so that it becomes more of a paint by numbers exercise when things actually arrive. So you'll see as I go through some of the components today, and I'm explaining some of the considerations that go in, just how much work does go in to those early stages. And so by dealing with those problems before they happen, by working before you even manufacture anything, working with engineers and fabricators together to solve problems, we can really simplify things by the time that we get to the final build. The systems I'm going to look at today, predominantly I'm going to look at floor systems, a little bit of walls, roofs, not so much, but I will touch on it. So like I mentioned, I want to explain, I think a lot of you have probably seen lightweight floor truss systems. What I really want people to understand is some of the complexities that are in there. So it's not just a simple matter of choosing, okay, I'm going to use a lightweight floor truss system and all my problems are solved. It is really important to engage with an expert, with a specialist provider, so that they can deal with these issues upfront, and so you don't have any trouble as you go through the project. So if you haven't seen these prefabricated lightweight systems before, they look pretty simple. Like most things, the devil is in the detail. And if you get it right, then absolutely it is a simple system once you get to site and you are installing these. So there are certain considerations to these sort of prefabricated cassette systems versus just using single floor trusses. So you really need to look at the project more holistically, think about how you're going to break up this system for the flooring, what's the sequencing of how these are manufactured, how they're sent to site, how they're installed, how does this whole building come together? And if you do that thinking up front, it becomes a really simple process once it gets to site. The details around the end connections of the trusses are really important, understanding what you need those trusses to do, what loads they need to transfer, how they need to connect into the rest of the building. And you'll see there are a lot of options there that can be implemented into a cassette system and a truss system. Think about the lifting systems and making sure that the installation has been thought of through the fabrication process, and also the manufacturing and what sort of tolerances are required to ensure that everything fits properly on site. So a cassette system provides basically a panelized system for your flooring. Usually it is with open web truss systems, and we'll talk a bit more later about the advantages of doing that. There's a lot of flexibility here in terms of the materials and finishes that you want to use depending on what sort of performance requirements you have for that floor. The lifting components are all pre-installed part of the fabrication process. You'll see them delivered in stacks on a truck, and that the whole sequencing of how those are sent to site will have been thought out to match what needs to go off first, what needs to get installed first. On larger projects, you'll likely have a crane, a tower crane or a mobile crane that's been permanently in place for the project. For smaller projects, you may be able to use a crane truck to do the delivery. And this is a bit of a plug number, but an average of 2 to 4 hours is sort of what we adopt for installation per level of cassette flooring. And so you can imagine that kind of time frame compared to trying to pour concrete over a level and finishing it and waiting for it to cure, to go in the space of maybe 2 hours to have a workable, safe, stable platform that you can immediately walk on, work from. You can really see where the speed advantages start coming, and how quickly you can get projects up when you're using this type of system. So looking a bit more detail on the open web floor truss systems that are available, and this is one of the CPD questions relates to this. So basically 2 options. One is a full timber truss, our version is called a long reach, and the second is a metal web truss, which is our Prida span. So the long reach trusses, the full timber trusses, they tend to be more robust. They're a more heavy duty solution. You can manufacture them in any depth, although usually between 200 and 600 mils. They are the premium solution in terms of performance and stiffness. So for heavy duty applications, big loads, challenging dynamic situations, the full timber solution tends to be the preferable one. You can include things like set downs for bathroom areas, and you can achieve some fairly significant spans up to 7.4 meters with these. Metal web trusses are more of a modular unit based on the depth of those metal webs that are prefabricated. So they come in set heights. They're a really lightweight solution, very economical with the way they use the combination of steel and timber. Again, you can include set downs and all those features that you need for different parts of the building. Though the spans are slightly shorter because it's not as robust a solution or as strong a solution as the full timber trusses. So the process of producing an open web truss, so various machinery to automate that process, as I said upfront, provides a lot of precision in how they're manufactured, so you get exactly what you're expecting once it gets to site. Huge advantages to an open web system versus a full timber I-joist system or perhaps a structural steel, where you don't have these penetrations, these openings for services, and that allow for that, just avoiding problems coming up on site, because you don't have to do excess cutting, additional cutting. If you plan these things out, there's plenty of room in those trusses to fit services through. Various options for how you detail the ends, like I mentioned, to get the structural requirements and the connections. You can deal with loads being applied at various points on these, so you can manage structures where you've got offsets and cantilevers from upper levels down to lower levels. And as I mentioned, it's easy to plan in and detail set downs in these trusses to suit shower areas and bathrooms or balconies. In terms of flooring options, you've got a range to suit the applications that you need. So in the upper floors, you might see things like particle board and OSB. As you go beyond 3 or 4 stories, you might introduce stiffer solutions like plyboard, which can give you better diaphragm action versus a particle board solution. And then there are obviously other options available depending on what you need that floor to do, whether you need extra acoustic protection, whether you need additional dampening because of the dynamic effects. And it doesn't have to be a wood, the timber solution either, so cement toppings and things are also available. Ceilings, similar requirements, and it really depends on what the architectural needs are for ceiling heights and for finishes. So once again, you've got that flexibility of the open web system that you can mix and match a lot of different materials, and really it's all about making sure the requirements are understood upfront. And so you're setting the project up for success in the yard and even before you fabricate by understanding the architect's intent, understanding what you need the performance requirements of the ceiling system, and so that what you fabricate meets those specifications exactly and is easy to install once it gets out to site, and including integration with services and things like that. In terms of manufacturing, transport tends to be the limiting factor. So it really becomes a trade-off discussion if you want to stick to conventional trucks, conventional loads, and not requiring additional controls, and it's usually 2.7 meters wide and typically 8 meters long, although in that case it's more a limit of machinery. And so depending on what you need, there might be fabricators available that can do longer units, up to 12 meters long if they've got the machinery to do it. You can also look at wider cassettes, wider panels. Again, it's that trade-off conversation between the availability and the simplicity of the transport versus the additional speed you might get from breaking it down into fewer cassette units. So once again, important to identify an experienced fabricator that's done this and can give you those different options and understand the most efficient way to break up the project. The manufacturing of these systems varies from fairly simple manual methods right up to some fairly advanced automation. So it's pretty typical, a simple manual method here, and you can manufacture in this way. Your more experienced, more advanced fabricators will have some additional controls in there, so precision jigs like this one to give you perfect right angles and connections on your trusses. You might also see additional guides in place that allow really rapid, precise prefabrication of a cassette system. And like I mentioned, it goes all the way up to fully or almost fully automated systems. And so you might be able to produce one of these things with just one or two people and have some incredibly smart and very efficient machinery that can just pump out these sort of components very quickly and assemble these components rapidly. So I mentioned the various N-type options that are available. So it really does come down to the experience of your engineer and of your detailer to make sure that you've got the right combination of these elements in place, I suppose. And so you do need to think about not just the installed or final condition, but also the process of installing it. So thinking about the stability of the cassette, how it performs during lifting, depending on where it might sit in the structure. As loads are transferred down, do you have to think about crushing and robustness in those end connections? The key point here really is the flexibility of these systems. So whatever you need that particular floor truss to do in terms of its structural performance or what it needs to connect to, there's going to be a way of doing that with the timber system. When it comes to installing these systems, so a variety of different lifting options available, from fairly simple wraparound strap systems to pre-installed lifting hooks or lifting lugs that you can use. There are a range of proprietary options available on the market, usually just a 4-point lift. And as would certainly advise, especially coming from a background of doing lifting design in the precast world, is just make sure that extra care is taken with this process, that you do get expert input into lifting, because it's certainly one of the most dangerous parts of the installation process of any prefabricated element. And there are a lot of things that aren't readily understood. And one of the things I came across quite frequently was understanding that if you are picking a 4-point lift with 4 fixed chains, you're actually only loading 2 of those chains at any one point in time. And so you have to make sure that all of your lifting points are designed to take half of the load of half of the weight of that unit. And it's little things like that that are, I'd say, more commonly misunderstood by a layperson, and they might see a 4-point lift and just assume that that's equally distributed to all 4 loads, and it's only if you've got the rigging required to do that load distribution that you actually get that performance. So make sure that there's you're using a reputable supplier that has experience in doing these lifting designs. Otherwise, things can go very wrong at that final stage of installation. So this is kind of a complicated slide. You don't need to understand all of the equations and calculations that go on here. The point of showing this is really just to show the importance of understanding the systems and how to get the most out of them, and getting that engineering input to make sure that these floor systems perform the way that you need it to. Particularly in a mid-rise situation where you might have customers and end users that are used to living, occupying a concrete building, and they're used to the feel of a concrete building. So you need to make sure, as a serviceability requirement really, that the inhabitants of the building don't feel uncomfortable, and that can certainly happen if you've got too much flex in your floors and too much bounce, too much dynamic performance, or too much dynamic behaviour. So the Australian code are fairly simplified, I suppose, when checking for dynamic performance. And so typically you look at overseas codes for some guidance on how we do this. So the European codes, for example, and this is again one of the CPD questions, we're looking for a fundamental frequency of at least 8 Hertz in the floor system. And we'll sort of do a quick worked example after this. So this bit is sort of like an engineering lecture. Again, it's not crucial that you understand all of the processes of the calculations, but really it's more conceptually understanding the systems that are in place and the different the factors that go into determining how a floor is going to perform underfoot and dynamically. So what this is really showing is the impact of how the truss is supported. So in this first situation, we have our timber floor truss with 2 fixed supports. And so working through the calculations, we get a natural frequency for this system of just over 11 hertz, so comfortably above that minimum 8 hertz, and so we can be confident that's going to be an adequately performing floor. If we change that up and we introduce a steel supporting beam, so we've introduced some flexibility into the system of allowing that end to move as well, you can see that the frequency is now dropped from that 11 hertz to 9 hertz. And so we're starting to get to the point where you're starting to wonder whether this floor is actually going to perform as we need it to, and whether that additional flexibility might cause issues. And then if we look at converting both supports to that steel support and introducing that flexibility on both ends, now we've actually dropped below this minimum of 8 hertz, so only 7.85. So in this situation, we need to take a bit more time. We need to go have a look in detail at those other codes, do a more rigorous engineering check, and make sure that if you're a detailer, or if you come across a situation that you are seeking advice from the project engineer or from the nail plate engineer, if you're going through the prefabricated truss route, because otherwise you're not going to get that end performance for your end users that you'd like, and you sort of compromise the performance of your timber solution. So final note on floor systems and how it can improve floor dynamics. If possible, you can go to a deeper truss depth, but obviously that's not a decision that you'd want to be making late in the project. That's going to be a rude shock for an architect if you try and have that conversation by the time it gets to fabrication. So there are obviously trade-offs there, and you're increasing your floor depth and reducing ceiling heights. So you can do modifications within the truss envelope itself, so larger sections in the top and bottom chords, higher grades to improve their stiffness. You can add additional timber strongbacks that run perpendicular to the trusses. So they have an effect up to a point, but they can only do so much. You might need to look at the way that the building is structured and where you have spaces or supports in the building, and maybe if you rejig the layout of the floor trusses, run them in a different direction, you might find that the dynamic performance is actually improved with an alternative configuration. And if possible, if you have load-bearing walls available, extending the span or changing the way that you're breaking up the floor so that you've got continuous spans on the trusses can make a significant difference and give you a much stiffer feeling to the floor. So all of that said, there is only so much that you can do to the truss itself. And like that example we saw, it actually, in some cases, it doesn't matter what you do to the truss, it's the supports that are the critical thing. So you really do need to look at the entire system, follow that load all the way through, understand how the system is going to perform. And once again, it just points to that need to really engage. Yes, these systems are incredibly beneficial. They offer a great deal of benefit to projects in terms of that safety and speed and simplicity, but make sure you get the right advice up front and work with a fabricator that knows what they're doing and has access to that engineering support as well. So a little bit on wall systems. So prefabricated is generally the way to go, especially for these projects where you're sort of going up multiple stories and working at heights. They're typically a 90mm wide timber frame. In this example here, this is just an open frame where you'd actually complete the cladding and the final finishing on site, which is a level of prefabrication, but it's not the full package. And so there is additional time involved with using a system like this, where you do need to do quite a bit of site labor to complete the system. We can increase the amount of prefabrication by going to a more panelized system, and we are seeing this type of system gain a lot more traction, particularly in the higher multi-res projects. So in these situations, you are actually completing more of the work in the factory. So sheathing and cladding the walls, installing doors and windows, and so the once it gets to site, it's literally a drop and you're done. There's no more need to do any external work on the finishings or coverings. There are a tremendous range of options now available to these prefabricated systems. So not just timber either. There's a lot of, whether structurally or architecturally, the finish that you want, the performance that you need, there's a range of things you can do. So from your conventional OSB or ply to lightweight solutions and foams, Hebel panels, architectural, brickwork looking finishes, there's a tremendous amount that you can do things that would make you think that there's no way that it's a prefabricated timber frame, and some really clever solutions that are out there. So by all means, don't think that the architectural requirements might discount timber because it doesn't look like timber. There's actually a range of things you can do. All of that said, there are situations where some site framing might be unavoidable. And so an example like this, where you're trying to fit framing into existing structural steel, so the tolerances are incredibly tight, you're likely going to need some flexibility to adjust things on site and do things to fit what's there rather than what's on the plans. So the point of this slide is just to say that 100% prefabricated isn't necessarily the best solution. While there are certainly benefits to prefabricating elements and looking to maximize the amount you can prefabricate, it also needs to be some common sense applied that maybe 100% prefab isn't the way to go. So again, looking at that whole project, how the whole system is going to come together. And if you do have a situation like this with structural steel installed before the timber framing is going in, it might be better to site fix or site build that sort of those framing elements. So looking at how walls get made and get shipped to sites. So similar to what I showed with the flooring. So a range of options for prefabricating in the factory, from fairly simple manual methods to fully automated machinery. The more automated systems, obviously, you get the advantages of the speed and efficiency in production. And so if you can do more modular repeated elements, you really start to see the savings and the benefits of that offsite systems. You do need to think about every step from the factory to when it gets installed, and that's the same for every prefabricated element. So for walls, usually they are fabricated horizontally, designed to be stored and transported vertically. And so that once you get to site, it's just a simple vertical lift. Depending on the width, you might need additional things like spreader beams. Again, make sure that you've thought about those lifting requirements and engage someone that understands the lifting requirements, so that things don't go horribly pear-shaped right at the very end when you're just installing on site. So a few things to think about when we're designing these prefabricated walls. So, I mean, the usual timber requirements for creep and shrinkage, they become amplified when you're dealing with multiple stories. So making sure that you've thought about those sort of things, as well as the impact of loads moving down the system, and particularly for those lower floors, dealing with additional weight coming down, making sure that that's a design consideration, and that you are liaising, well, the fabricator and engineer are liaising to understand those requirements. So what that might mean is that the traditional lightweight timber framing is more common at the top floors, but as those structural requirements become more intensive, as you move down and those loads increase, you tend to see a shift towards the engineered wood products like LVL, those stronger species, those the EWP species that can handle those kind of loads without crushing. So for stabilized, so bracing systems, once again, you can use a timber-based system, and so this is one example of so similar design to floor trusses, but oriented vertically. To get you can get some incredibly robust capacities out of this type of timber bracing system. So you can use the sort of conventional like plywood sheathed walls that you might see on residential projects and just detached homes, but particularly as you go further down a mid-rise structure and as loads become larger, we do need to move to some of these heavier duty solutions. And so there are options in this offsite timber prefabricated solutions. So these are some of the things that we offer. We do limit the capacity. So we limit the published capacity of some of these units because, yes, the truss can handle a heck of a lot of lateral load, but you do need to think about what happens at the tie downs. And so a bracing system that's taking a large lateral load is also going to impose a really large concentrated load onto the slab or onto its support, depending on how the structure is built. So we do limit what we state that those units can claim. It's not actually limited by the capacity of the brace. And if you do engage a structural engineer who can look at the whole system and how it's supported and can design those base connections to make sure they can withstand the loads, you can actually go quite a bit higher than the published capacities for those. Not all fabricators will be able to make every system, and so there are a few different options, and depending on how strong the loads you need the bracing system to withstand, there are different options that you can go down. So this one here is a 10 kilonewton portal, so two relatively light duty floor trusses with an LVL header and tie down rods. So as I mentioned, there's those concentrated loads to transfer those loads down to the foundation could be quite significant. So you do need that heavy duty tie down system as well. This is obviously a longer span, a 15 kilonewton portal. This has got the heavier duty units. You can see the size of the nail plates compared to the light duty option. And then the other option, so this is getting away from a solid timber header, but actually using a full truss system. So not unlike a floor truss or roof truss, but actually designed as a portal frame, fully nail plated system that's sent as a modular unit, just like that. And so that's a 20 kilonewton unit, so double the capacity of this lightweight one we saw before. I'll touch on roof systems briefly. As you'll see, the typical mid-rise roof, it sort of doesn't quite lend itself to what we would, Pride would typically do for roof trusses, which is more of a, a pitched roof type system. So it's not to say that you can't prefabricate, and you certainly can, and there's been some great examples of it. But there are some challenges and things you need to think about. So often you're limited in your height, which, as I say, takes you away from the more traditional trusses you might see on a house build. So there are a few things that you need to consider to make sure that a prefabricated truss system is going to deliver what you need, and make sure that all these things have been thought about. So do you have, I guess that there's some key differences between a detached house of 1 or 2 stories and mid-rise project. So the air conditioning units are going to be larger. You may have large solar arrays on the roof, which introduce additional loads. You could be dealing with a much flatter roof system, much lower fall, and that can introduce effects of ponding from rain or hail or snow. So yes, you can prefabricate your roof system. Once again, I think this is probably the consistent message through the whole thing, is make sure that you get the right engineering advice up front, and make sure that all these things have been considered so that it performs the way that you need it to perform. Well, there's just a few examples of really taking that idea all the way through. So we saw flooring done as a cassette. There are ways, if it works out this way, and if it's the most efficient way, you can actually create modular roofs and just lift in place entire roof assemblies, which is pretty impressive. And beyond the timber roof trusses, there are also a range of different systems and other proprietary systems available. So I would encourage you to have a look into that as another option. So that's the timber options and what timber can bring to the table. I've sort of wanted to spend a little bit of time on my previous working life in precast concrete and have a look at the differences, I guess, that I've observed, and how does precast sell into the market, and how can timber compare and contrast with it. So a couple of the worst examples, I suppose, just to start. And I'm not here by any stretch of the imagination to bash the world of precast. I think that would be pretty disingenuous. I worked in that industry for a number of years, and I slept perfectly fine at night working with these systems and being responsible for them as the engineer improving the lifting and installation of these. But I do include them to show that when precast goes wrong, it has a tendency to go very, very wrong, because you are dealing with incredibly heavy units and they are difficult to repair. We'll sort of get into that in a bit later, but these are just some examples of things that have gone wrong and that have been the subject of WorkSafe alerts and things like that. So when you get the lifting wrong, and I've talked a bit about why lifting design is so important, you can get issues like this. When you have issues in fabrication or in transport, there's a number of moments there when all of a sudden your beautiful precast element suddenly doesn't look like it did when it came out of the mold. Here's another couple of examples of things gone wrong in the world of precast. So again, incorrect lifting leading to broken panels. And this one here was actually a SafeWork New South Wales alert of a 14-ton precast L-beam that was incorrectly rigged and actually dropped it. Thankfully, no one got hurt in that process, but it just highlights the incredible risks and the need for expertise in the world of precast. And like I said, when things go wrong, precast, they can go very, very wrong. In terms of my credentials to talk in this space, so basically the role that I had, I was on everybody's speed dial the moment anything went wrong. So whether that be the contractor, and we worked with some of the the real majors like John Holland and Multiplex, the CFMEU, the unions obviously had an acute interest in any safety issues on site, so they'd be calling me if anything happened or if they thought there was a risk of something going wrong. The precasters, WorkSafe, hopefully not, and we had some really great proactive conversations with WorkSafe. You definitely don't want WorkSafe calling you after something has gone wrong, and the National Precast Association as well. So, myself and my team at Reed, our job was to stop problems before they happened, and for the most part, we did that really well. Then the other part of the job, which is the trickier, more stressful part, is fixing them when things do go wrong. And so some of the things that can happen in the precast process and issues that we saw fairly commonly, spalling of concrete. It's not particularly receptive to knocks and things during lifting. Cracking and spalling around edge lifters, which is obviously a concern for installation. Lifting devices not installed correctly or modified. And I mean, once something goes wrong with a precast panel, it's very hard to fix it. There are post-install lifting solutions that you can use to get something in on site, but they are you're damaging the panel, you're changing the look of it, changing the finish of it, and so and they're not as easy to install as well. One of the things about precast is you're often, the way the connections are designed, you've got long dowels, reinforcement sticking up from the top of the panel. You need the next panel to come down perfectly straight to slot on, and if it's even at a slight angle, 2 or 3 degrees can be enough for those dowels not to fit in properly. So as soon as the planned lifting system doesn't go right, you're in for a lot of complexity to try and get that in. So some of the challenges around precast. So it's obviously a brittle, concrete brittle material. So when failure happens, it happens really suddenly compared to timber. It's obviously dealing with much heavier elements, so it's not uncommon to be working with 10, 15, 20 ton elements, which means you need larger cranes, and obviously there are higher risks when things go wrong. I think we all know concrete's weak in tension, and so the nature of, well, one of the challenges of prefabricating concrete is that you are casting it horizontally typically and then lifting it vertically, and you're doing those things at the weakest point of that, a very early age concrete. So there are issues around cracking that can happen during lifting. It can also happen during storage. If you store precast concrete in the wrong way, in the wrong environmental conditions, you can get surface cracking as well, which obviously is a concern. When things do go wrong, they are difficult to repair, especially on site. If you send a precast element to site and then find that something's wrong, usually there's no way to safely store it there, so it needs to bring a truck in and send it back and do the rectification in the yard. So you can't. I think one thing I've certainly observed with timber is it's so much easier to do those quick changes and repairs and things on site. The requirements around lifting and bracing are quite complex in the world of precast, again because of those safety considerations. So every single lift needs to be signed off by an engineer, which is me and my team, and the temporary bracing also needs to be designed. And so it introduces a number of stakeholders that go into that installation process, and so it's a lot of coordination up front, because it's often they're different parties, and there's a lot of confusion in the industry. Actually, I presented a paper last year to the Concrete Conference around the intention of the standards to have one engineer that looks after that whole thing, and then the practical implementation of that, which is often you've got a lifting engineer and a bracing engineer, and you may have an engineer embedded in the project team as well as the contractor safety committee and the union. So a lot of people with acute interest in what's going on, and so a lot of coordination up front, and certainly if something goes wrong or if things don't go as planned, there's a lot of work to be done to get things back on track. And some of that confusion is due to conflicting documentation in the market. So there is an Australian standard. There's also a national code of practice, which some practitioners, some states like to use. And then down here in Victoria, we have the Blue Book, as it's called, which was the WorkSafe guide. And that's, for the unions, that's their Bible. And so there are conflicting methods and conflicting requirements in the Blue Book compared to AS 3850, and so that can lead to delays and some problems on site if that's not understood and communicated properly. So I guess I do want to make the message before we get into some questions that none of these things are inherently bad. As I said, I'm not here to bash precast as a solution, but there are complexities and they do need to be managed. And I think for those of us who are really looking to advocate for a timber alternative and see timber increase its use in construction and in projects, then these are all things that perhaps you weren't aware of, and they're all opportunities where you can introduce the conversation about timber and compare the advantages of timber to precast in some of these situations. So I'll open it up to some questions, and Paolo's going to give me a hand with that. If you want to grab a screenshot of that before Paolo takes the screen share back, there's my digital COVID-safe business card, and certainly happy to talk to anyone after this.
I think we can stay on this slide for a while. And
sure.
Really interesting presentation, Adam. I think your experiences in the field of precast is very, very valuable to Pride and to all our community in order to quantify the advantages that we know offsite prefabrication in timber components already offer. But with your support, I think we can do another step and really leverage all these benefits in a more comprehensive and a more formally correct way. So I encourage everyone who has a mid-rise project and considers using prefabricated timber components to contact Adam and leverage his experience into this field, because that's really where the main advantages come from. We have seen this in many projects that the rate of installation is faster with respect to equivalent concrete designs. And there is a whole list of projects into our technical design guide 50, which is the cost engineering guide to describe it in many projects in Australia and overseas, America, Europe, etc. But the reason why this is happening, so people are not rushing. The reason is they feel safer on a timber construction site, and therefore, at the end of the day, with no props, no reel, no cables around, so no tripping hazard, at the end of the day, the rate of installation comes up to be quicker because it's safer. That's the reason why. So let me have a look at your question. And Adam, can you please also click on the Q&A button and have a look at the question from our attendees? The first one from James Stephenson, is, please do a brief refresh on the durability of the Prida connector plates. Do you have information on that?
Yeah, so all of our plates, as a minimum, have a Z275 coating on them, and so they're suitable. So a galvanized coating, they're suitable for situations where they're going to be in an enclosed environment where they're not going to be wetted and dried and they're not exposed to salts. There are options. So for applications like in-ground applications, we've got heavier duty like a Z500 or Z600 coating. We've also got a stainless steel range on connectors that can be used when you're dealing with close to breaking surf and salts and things like that, or repeated wetting. So yeah, a range of things available for different applications, and the main thing is just to understand what the environmental conditions are and choose the appropriate level of protection.
Yeah, perfect. Then the second question from Jerry Howard is, if a screed or concrete topping is specified to receive ceramic tiles, would stricter deflection tolerances be specified? And would it be critical for the designer to be provided with this information up front? Yes, certainly, yes. And I don't know if you have a specific question for this. What I can say, screed and concrete topping are not the only option to add some mass. There are ways to add some mass for controlling the vibration and the acoustic as a dry mass. A lot of examples, also some of them well shown in our demo building in Holmes Glen TAFE, which is visible physically now that the restrictions are being lifted a little bit, but also it can be visited online from our website. There are photos, there is a video, etc. So, but up to you, Adam, if you have any specific answers to this question.
Nothing specific. I think it just ties into that importance of having the right conversations early in the project.
Yeah, perfect. So then Lisa is asking about time saving on site versus connection cost. There are some fancy European connectors for rapid assembly which are costly but might save a lot of time. What's your rule of thumb? Wow, difficult to answer in general terms. Every project is so specific, is so different. In mid-rise, really every project is quite different, as you know. So look, I think in Prida's case, they have a very well broad and well detailed set of connection, and Adam showed something. For instance, the what is called the drop downs for the balcony areas, for the bathroom areas, set downs. Huh? So Adam, up to you.
Yeah, I mean, I guess my rule of thumb is if you can pre-install it, do it offsite, then do it. The challenge can be in selling that value and having that conversation. So it's all good for me to understand the value, but can a fabricator convince a builder or a developer that the time savings are real and that there's money attached and that it's worth paying a premium for the fabricator to do more labor in the factory? That's probably more of the challenge. We know that the connections can save time. We're absolutely convinced of that. It's a matter of then communicating that message to other stakeholders in the project and getting them to pay for it.
And that's the typical case in which our MAP advisory is really of an help, because we are non-commercial. We can help you optimizing your project and using the right connection for the right location within your project. Mixing, because that's really a big advantage of timber design. You can mix and match different components and different products to suit the specific of a part of your design, of a part of your project, and all the products are compatible to each other. They have similar tolerances, similar easiness of installation. So don't be scared about mixing and matching and optimizing your project, because this is the beauty of a timber design. So then we have David Mayes. How does cost of timber framing compare with solid timber CLT for similar application? I think I've already answered to this. If you use the right product for the right position into your design, that's where your cost efficiency lies. Some parts of your project need CLT. CLT is the right material for that. Others really would benefit with a cassette floor approach. And so if you choose the right one, we have, for instance, guide number 46 in our technical design guide range, which illustrates how to mix and match. And it's a really easy to understand with a lot of graphics, a lot of span tables, etc. So I encourage you to read that and refer to us as MAP advisors for this. Adam, comments on this?
Yeah, it kind of goes into my favorite LinkedIn hashtag that goes around of what is good when understood. And Perfect. So when you're, your upper floor, conventional 90mm radiata pine will likely do the job perfectly well. As you go down a building and those requirements increase, you may well find that those the more solid timber options are more cost effective. So I guess I just want to see as much built out of timber as possible. And so whether that's lightweight framing, whether that's a CLT or a glue lam or whatever it might be, yeah, just I guess what I hope that people got out of the presentation is understanding that there are some lightweight options available and where those play and where they're the most efficient, but obviously they're not going to be the be all and end all.
An interesting question from Viet Truong is that one of their project has an issue raised by the builder that the lightweight flooring system does not have enough bracing capacity to hold the precast concrete panel walls on boundary sides of the building. Do you have any information regarding these issues? Mine is try to avoid the concrete wall panels, and you can do the same in light frame for the boundary walls. It has been done. There are very good examples about it. But I mean, if it's too late, I don't know. Maybe Adam, you have an answer how to improve the bracing capacity?
Not off the top of my head from that level of detail.
Yeah, we need to see. Maybe Viet send us the drawings and we have a look. Sergey, are these requirements for the builder to load the cassette floors with dense coverings for acoustic purposes? Our apartments were built with cassette floors, but sounds like the builder did not put any acoustical treatment and can hear neighbors really well. Sorry for that, but we sent independent acoustic consultants doing measurements on site after completion, and they found out that the as-built values, where everything was done well, including the sealing of the penetrations, which is really critical, but the as-built acoustic performances were better than designed. In at least 2 cases here in Australia. I've done it in Italy in 6 or 7 cases as well, and always we got results which were more favorable, better than it was designed, which is normal in engineering. We tend to be, how can I say, on the safe side when we design. Adam, any comment on this?
No, you've nailed that one.
Have a look at another one from an anonymous attendee. We have another 2-3 minutes, but we can extend a little bit. Adam, for a mid-rise timber building, how typically does the project structural engineer interact? Do the Prada engineers do the engineering, etc.? That's for you.
Yeah, so I guess the final detailing and design, so through our Prefabricated software that goes, connects out to the factory into the saws to cut all the members and things like that. So that needs to be used by someone who's trained in that software. So that detailer would then engage with the Prado engineering team around the specifics. So I would say that upfront engineering, it's easiest if the decision has been made earlier in the project to go with a cassette system or open web trusses or whatever it might be. Do the preliminary work to understand that system is structurally adequate, and then the nitty-gritty details around getting it into Prada build so that it can go out to the saw, that it can get made in the factory. That'll be done by a Prada detailer.
Good. And also the next question is interesting. I think we have time for both the last 2 questions. Can you tell us a bit about fire rating on connection plates and nails? There's a lot in our technical design guide 37, but also certainly in Prada's technical documentation about this.
Again, it's probably not something I have done a lot of work on yet, so I would be referring to those published technical.
Refer to our technical design guide 37, which is the deemed to satisfy detailing. You can use them also within a performance solution, of course, because there's nothing against using some DTS details in a fire engineering report. On the other hand, it's appreciated. And the last question is also interesting. How high can you typically build lightweight timber apartment buildings? How many stories are cost effective? How do you deal with the lower story walls that are more highly loaded? Okay, I will answer to this because there's a lot of experience also in Australia doing 5-6 stories. A lot of experience in America. We had our last week webinar reporting about what's going on in America, where this is really, really typical. But also in Australia, we have some case studies of, I think, 5 or 6 at least projects built by a major builder here in Australia, and now it's becoming popular also with other builders. So dealing with the loads, I mean, it's not difficult. It's like in every other material. You densify the studs, you make them closer and higher in number. You take more care about the crushing of the timber which is loaded perpendicular to the grain, and therefore you move towards more a balloon frame type of construction and detailing as opposed to the platform frame. A lot of this is very, very well described in our guide number 50, which is the structural design, and covered by, for instance, my colleagues Adam Jones and Dean Ashton. They are specialists into this. So please refer to us with your projects and we will give you the answers. No problem at all. Okay, so feel confident up to 5-6 stories. Above that, probably you need to start introducing some CLT and LVL into the mix. I think we are right on time. So I will switch to my screen just to conclude, and that's it. And so this was the Q&A question. Next week, we have another of our partners, Rotoblast, which is presenting on innovative connections in CLT structures. As I said, materials are complementary to each other. They can be mixed. So this will be another very interesting presentation from a guy with a lot of experience. We have wonderful videos that show how things are made on our website. I encourage you to have a look at these videos. They are really, really good. And so without further ado, I thank you for your presence. I thank Adam for his excellent presentation. And I hope you will join us next week for another interesting webinar before probably we reduce our frequency a little bit. Look, I'm not sure about the calendar for the coming weeks after this, but I think we have another 2 or 3 in the series, and then summer is coming, you know. So thank you, everyone, and feel free to contact us anytime for your queries. Have a good day.